Dear friends, good evening. Happy Easter to everyone. As all of you know, Maths Aspirants is a collective of math people, math students, research scholars, and faculty members across India, started by myself in 2017. And we used to organize several online programs to help the students who are preparing for different national level competitive examinations like CSER, NET, GATE exam, IIT JAM exam, and other PhD and PG entrance exams. As a part of such online problem solving session series, we now plan to organize a session, a series of classes, online problem solving sessions in the area of metric spaces that will be helpful to students, especially for preparing for ISI MMath entrances, and also for all the students who are really want to clear CSER, NET or GATE. Everyone will be get benefited, I am sure that. So we blessed to have Mr. Abhirup Das from West Bengal today with us to handle the session. He will discuss on metric spaces. I think we will have our session in 4 or 5 sessions in the coming days on various topics related with metric spaces. Mr. Abhirup Das is currently doing PhD in mathematics at TCG CREST, Kolkata. He cleared CSIR NET with JRF and GATE exams. And he did his MSc from University of Burdwan and BSc from University of Calcutta. So I would like to express my sincere gratitude to Mr. Abhirup for accepting our invitation and agreeing to handle such sessions for the students. I'm sure that these sessions will be really helpful to anyone, those who are seriously want to pursue higher mathematics. I welcome everyone to this program. Welcome, Abhirup.
You have said a lot of good things about me, actually. Okay, so I'm really grateful to you for that. And I mean, gratitude is to be shown from my end to you because of for giving me such an opportunity. Because you see, I mean, as I told you that we have also started an institute, and just I mean, it's nice to see people who are really interested in mathematics, because I mean, I'm not against any topic, or I'm not really trying to belittle any topic, but I'm just saying that maybe because of the inflation and all those things, I mean, I believe more and more students are right now inclined towards those, I mean, the courses which have a corporate exposure. I mean, BTech and MBA has always been there for the last 2.5 decades. I mean, in the recent history, data science is there. So it's really, I mean, it's really refreshing to see that, I mean, all of a sudden, I mean, within 4 to 5 minutes, there are 30 people joining this session. I mean, it means, I mean, we have hope. I mean, that's all we can say. If sir is still there, sir, can I ask you something?
Yes.
Sir, I told you, I mean, a problem session. I mean, the assignment was there, but I think I told you that we will, this is sort of a path that we are supposed to follow. But I mean, I tend to keep my teaching sessions a bit spontaneous. I mean, I would like to take questions. I would like to give in my instant inputs wherever, if there is one. So since we are starting from today's topics are related to sequence and series of functions and Riemann integration. So I mean, I was just fascinated. How about if we start from fundamental theorem of calculus? Because since from class 12th level, I mean, that was a fascinating question, because I mean, in 12th syllabus, first we are taught how to compute an integral. That is just integration of x to the power n is that, integration of e to the power x is that, and integration just was a set of formula, and that's it. And then suddenly in class 12, we came across something called definite integral. Then we saw that if you just put limits in the indefinite integral, we subtract it, suddenly we are getting the area. So one natural question that struck my mind was that what is the connection? One was antiderivative. And once we are putting in the limits, we are subtracting it. It is giving me an area under a curve. I mean, what is the connection? Apparently, they are two very different propositions, right? I mean, whenever we are integrating x, we are getting x square by 2. And then somebody is saying me, well, if you integrate x from a to b, then you get the area. And the formula is that x square by 2, you just put by a square by 2 minus b square by 2. So this is, I think, the most fascinating concept to start with in integration, that how an area is connected to the antiderivative of a particular function. So am I allowed to start with that? I mean, I think that particular thing is sometimes we miss that.
Yeah, sure, Abhirup, you can set as you like, no issue.
Okay. So thank you for giving me the liberty, actually. Okay. So let's start with that. So, I mean, let's start with this fascinating concept. I mean, a concept that I found pretty intriguing to start with. So, in class 12 level, maybe at 10+2 level, we came across two very different notions of integration. One is definite. This was, I believe, in class 12, and another is indefinite. Okay. This was, I believe, in class 11. So in one, you were just told to integrate fx dx. There were not any limits, I mean, below or above the integration sign. And you are told that you will get a function, maybe I should write ft dt. You will get a function ft dt. You will get ft. I mean, the property is that f prime t is ft plus some constant. Okay. So that was the first notion of indefinite integral. If you just open a book of any class 11 book, you will see this notion first. And then in the definite integral, we were told that suppose this is a curve, you call it f, a be the point, b be another point. Okay. Then we were told that if you integrate a to b ft dt, this is nothing but fb minus fa, right? And which is also, and infinite integral was by definition area under the curve. So apparently these two have no connection whatsoever, right? One is indefinite, one is an antiderivative. Let's call it an antiderivative. Antiderivative. Or sometimes it is called in the complex analysis as primitive. So why all of a sudden this thing, I mean, putting the terminal values in the antiderivative, in the primitive, and subtracting that, why should it produce the area? So that is apparently, I mean, not so clear. So what we started doing in BSc, we sort of reversed the concept. That we define, step one was define the definite integral first. On AB, a closed bounded domain. Okay. And how was it defined? So it was just defined as we did on the class 12 level, just with a little bit more rigor. So this is A, this is B, and then we are considering a partition. Okay, so call it P, a partition of AB. What is a partition? It is a set of points. So call A equals to A0, then you A1, blah, 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 up to AN is just B. Okay, so this is a partition. That is, you have partitioned this domain. Okay, and what were we doing? What were we doing is that we were drawing these things, and we were considering two sets of rectangles. One, this one, and another, let me choose another color, this one. Okay, and this is same for every triangle, I mean every rectangle. Okay, so when we are taking the upper rectangle, what we are doing? So you see, when we are taking the upper rectangle, I mean, take any rectangle. Okay, take this rectangle, take the ith rectangle. So what is this area? This is nothing but ai minus 1 times mi, right? Where mi is infimum fx, where x in this domain, right? And for this upper triangles, the bigger triangles, we have mi times ai minus 1, where mi is supremum fx, x is in the same interval, right? Now you see, if we just join this sky blue rectangles, okay? So we are considering the sky blue area only. You see the sky blue area, I mean, that is this. Okay, so what is that? According to this partition, that is nothing but summation mi ai minus 1, right? I running from 1 to n. We denote it by UPF. U for upper sum, P for partition, and clearly F stands for the function actually. And this one, the set, I mean the sum corresponding to the smaller triangles. Okay. Okay. So what is that? That we define by LPF, which is nothing but
LP.
Right. So that was, I mean, that is how we defined. And one thing you can of course observe, that LPF is clearly less than equals to UPF, right? And also you see the area under the curve is in between these two. So area under F, right? Now this is true. See, P was arbitrarily chosen. So this is true for all partition P. Correct? Now we are doing one more thing. What is that? So you are doing another thing. That is, there are two partitions P and Q. We call Q subset of P if every point, I mean, let's write this way. If, so P is a partition, Q is a partition. So clearly a refinement will be this refinement. So Q is,
Sir?
if Q is P union,
Sir?
a few more points. Yeah.
Hello?
Yeah.
Sir?
Go ahead.
Sir, the
Yeah.
geometry that, sir, the geometry
Yes.
that, sir, the geometry that you, hello? Am I audible?
Mhm.
Hello?
I can hear you. Go ahead.
Hello, am I audible?
Yes, you
Yes,
are.
sir.
Go
Sir,
ahead.
the geometry that you have mentioned above, sir, the geometry that you have mentioned above,
Yeah.
it can be visualized if you consider a positive continuous valued function, because sometimes if we there may be such functions which are very critical. At that point, sometimes we cannot interpret this geometrically, that is LPF and UPF. So
No,
so
geometrically
that is what.
that is see, whenever we are drawing something, it means sort of we are assuming the fact that the function is continuous in some domain, in some interval of the domain, in some subdomain, right?
Yes, yes.
I mean, I cannot draw Dirichlet function. 0 for in Q and 1 in R minus Q. So I can't draw it. So whenever I am drawing
Yes,
this
actually,
line, I am assuming that there is, I mean, this is the function is continuous in this interval. So just to give you
yes,
that,
sir.
yeah.
Yes, exactly. That is what I'm saying. That sometimes we may get some typical functions for which we cannot interpret the geometrical. But if you consider a positive continuous valued function, then it is very easy to visualize LPF and UPF geometrically. The geometry that you have shown using rectangles.
And you see, I mean, the fundamental theorem of calculus that we are trying to prove, I mean, trying to establish the connection between, this is on basically continuous functions, right?
Yes.
Even
That
if
is what
so, even if it is negative, I mean, but it is continuous, so we can just go there and, I mean, take the negative sign, and that will work.
Yeah. For negative, I think we have to put actually modulus, and we have seen such examples also.
Yes. For the negative, I mean, he is right to point out this thing actually. If is positive in its case, because you see,
Yeah.
I mean,
And it should be continuous also within this interval.
yeah. If is positive
Yeah.
and continuous, maybe if
Then
CAB, I
then it
should.
is easily visualized geometrically. Yes, that's
Because you see,
that.
I mean, he is quite right actually. So suppose you take this function. So whatever you are doing here, this sum, I mean, then you will probably get the LPF is bigger than the UPF, right? That's what you are trying to say, I think.
Yes. Then
The LPF
then
will
it is
be bigger.
yes. Then it is very easy to visualize geometrically.
Yeah, but I mean, what we can do is that we can just go here, we can define it for the positive functions, and for the negative functions, we can define it for mod f.
Yeah. Yes.
Okay. That's very good of you to point out. Thank you. So what was I telling? So Q is a refinement of P if Q has a few more points than P. Okay. So one thing we can notice, we all can notice is that if, I mean, you take a finer, so suppose this is your P, okay, so this is your, say, okay, and you take, say, a finer partition, okay, that is your Q. So this is, say, what should I say, this is, say, give me some alphabets, so P1, P2, P3, P4, okay. So your P is A, A1, A2, A3, B, and your Q is P union P1, P2, P3, P4. Okay. So let's observe what happens to the LPF and the UPF. Okay. So let's use to okay. So yeah. Okay. This is my LPF for Q. It is there. It is there. It is there. Okay. And what is your L? This is, so this gray area is basically your LQF, right? LQF. What is your LPF? Let's see. So your LPF is, you look at it, this, right? Your LPF is this. It is this, right? And this, okay? So you clearly, you notice that there are extra areas in LQF, right? Like this area, this is extra. This area, this is extra. These areas are extra. These areas are extra, okay? So we can say that LQF LPF is less than equals to LQF, right? Right? But what happens to the upper sum? So now let's take the upper sum. So corresponding to this, the upper sum is this, right? Then the upper sum is, I mean, this again. But you take this upper sum, you see, the extra area is there, right? Right? So this is also clear from your side, that clear to you that this is U. If I'm not mistaken, this should be the case, right? A to B. Okay. So that's something we have. Okay. Whenever there is a refinement. Now, define. So if supremum of LQF, I mean LPF, this supremum is taken over all partitions. Okay. All partitions is equal to infimum of UQF. Sorry. It doesn't really matter because they are variables. Again, all partitions. So clearly, this is a real value. This is a real value. There are supremums and infimums. Partitions. If these two are equal, then we define integration a to b fx dx is equal to one of these two numbers. Okay. Equal to that. Okay, so call this, what should I say? Corresponding to f, let's call this gamma f maybe. Gamma f is a constant, okay? So gamma f. Okay. So that's how we define the definite integral, okay? Now moving on to defining the primitive. So how do we define it? Define if say if x, we are defining it to be b. Okay. Clear? Because see, this part is defined, right? Because right now you are considering this interval, okay? We can also define, see, I can be more rigorous here, but then it will take the whole class to do the single thing. So just, I'm sort of sketching the proof. You can also define fx to be minus infinity to x ft dt. Now there is a problem. How can we define minus infinity to x? We define the Riemann integration on closed bounded intervals. So this we will be taking as okay. Clear? So what do we want to prove actually? We want to show that we want to establish this connection, because clearly this is an antiderivative, the primitive, or maybe this is the primitive, and this side, the RHS, is nothing but the area under f from a to x, which is of course a function in x. We want to show that if prime x is nothing but fx. Okay, that is our goal. Let's see. So right now we are taking f to be continuous. Okay. So you see, let's compute what is fx minus fx plus h. So what is that? From there, you see minus infinity to x plus h fx. Right? So that is by our definition, limit a tends to minus infinity. Why did I write minus? My handwriting is horrible. Okay, so I just request you to tolerate this for the time being. I mean, for the next few classes. Okay, take the limit outside. It's nothing but I mean, someone was, I mean, who was it who just asked me the first question? I mean, I will ask you a question. I mean, if you are okay with that. So can you, I mean, can you just say hi or something like that? Hello? The first guy who asked me. Hello? Am I audible? Okay,
Yes,
so
sir.
I have
Yes,
a
sir.
question. Yeah. So can you tell me,
Yes.
could I just
Yeah.
write this? Could I just write this? From this, could I just write? Could I just write? Is this correct? I mean, can I just write it? I mean, of course we can write it, but I mean, what we have developed so far, okay, what we have developed so far using the Riemann integration, that theory, is this, can we just write this, is this equality well justified?
So it's
Shubhrita, are you in the class? Hello? Shubhrita, Rahul, or Arpan, I mean, are you in the class? Hello? Can you be a bit louder? I'm struggling to hear your voice. Hello? Okay. So, okay, see, she's one of my promising students. I mean, there are a lot, but I mean, 𝕨𝕚𝕚𝕚 is here, I think. Arpan is here. So, can you please tell me that can we write this line? I mean, is that okay?
sir,
Yeah.
hello.
Yeah.
Sir, if you interchange this limit, the range, then I think it can be done.
I mean, you are saying that we need to write this step first, then this step, right? And then this step, right? So you are saying this direction is okay, but not probably this direction, right?
Yeah.
But why not? That is my question. And what's the problem? I mean, that direction is right. That is not wrong. But I am just saying that we are not yet ready to write it. The theory is not yet developed that far. Shubhrita, can you please tell me why can't we write it? Hello. Hello. I think her network is not working probably. Hare.
Yes, sir.
𝕨𝕚𝕚𝕚, can you tell it?
No, I can't.
Okay. Shubhrita, are you, I mean, hello?
Yes, sir, I'm thinking of it.
Okay. The hint is in this line. The hint is in this line, okay.
Hello, sir.
Yeah.
Sir, as you just said, still we have not developed the notion of improper integral because Riemann integration only depending on closed boundary intervals. So
Very good.
we
Very
can't
good.
write this.
Very good. We can write this a to b f dx minus a to c f dx is nothing but c to b f dx, right? But that we can write because a, b, c, d, these are closed intervals. Riemann integration is developed on closed intervals. So directly we cannot write it. We are yet to establish this connection. So I'm deleting it, okay? I'm erasing it. I mean, Lopamudra and Subhrita, you can do better than that, I believe. Don't be so nervous. Okay. Don't be nervous.
Sir.
Yeah.
Hello. Sir,
Yeah.
there will be fx plus h in the first part, I think. I mean, at the first part, we have.
Right. Extremely sorry.
And another thing, sir, is in here, you have said that we can only write it. I mean, we can only use Riemann integration when it's in its bounded interval, closed bounded interval. So we should we define just that for the h part that it will also be in that bounded interval?
Yes, of course. So he is saying that if is a function from a to b to r, x is in this interval, then he is saying that x plus h is also in this interval. But that is assumed. You understand? I mean, h will be tending to 0 in a while. So okay.
Okay, sir.
So you see that now f is a continuous function, right? Right. So if you just put a mod here, what do you get? Okay. Can you observe one thing? You just can delete the limit part here because in this interval, I mean, it is integral, there is no a. So you can just write it. Okay. Because there is no a anymore. You see? That was the trick to get rid of the a. Okay. So now you just do this. Right? Which is less than right? Now you see f has a maximum in this.
Supremum given?
Sorry?
I mean, we as you have written here, the modulus part, I am saying is was there some supremum value given that mod of fx might assume maximum m or something like that?
I'm about to write that.
Okay, sir.
Since f is on this interval, which is a closed bounded interval, hence compact. So if we'll assume its maximum and minimum there. Okay. So will mod f. So it's safe to assume that mod f max, that is, I mean, the maximum value of mod x, say m, right? Let's take m just. So it will be.
And sir.
Yes.
And sir, hello. And sir, generally the function which is continuous on a bounded closed interval, the function which is continuous in a bounded closed interval, then surely it will attain its maximum. I mean, the
That's why you could write it. That's why you could write it. If f is continuous, then mod f is continuous, so mod f has a maximum. That's why we. Yes, please. Hello. Okay. Anyway, so mh. So that's what you have. Okay, let's adjust this tape for a while. Just a minute. Let's just adjust this tape for a while because I need there to be. Since f is continuous on since f is continuous on AB, we could say that f is uniformly continuous because of the closed boundary interval, right? So for epsilon greater than 0, there exists a delta depending just on the epsilon, such that if x plus h minus x, that is h, because h is taken to be positive, is less than delta, we have f of x plus h minus fx less than epsilon, right? That much we have. Okay. So tell me, what should be my next step? Anyone? What should be my next step? Hello. Hello. Hello.
Sir, I think the step which we have written here, mode of f of x plus h minus fx,
Yes.
which is less than or equal to integration x to x plus h, and the integrand is mode of f of t dt. This is less than epsilon times h.
Exactly.
So,
This is less than epsilon times h. Now you see, you just divide this part by h. Right? Not exactly epsilon times h actually. No, this is epsilon times fx, I should say. H fx, now that should be the thing, right? Only then you can just get the fx there, right?
yes, sir, yes.
Now you just tend it to 0 because h tends to 0, because you see h is less than delta means h is tending to 0. So now you have this. If prime x is sort of fx. Okay. Maybe we could get rid of this mod sign actually, I believe. This mod sign maybe we could get rid of. That would have been good enough, I believe. This is. Yes, I mean, we can do it in a more simpler way. That's, I think, will give you a better intuition at least. So f of x plus h minus fx, yes, that is x to x plus h fx ft dt. Now you see, I mean, what do you know? Since h is f is continuous, you have limit h tends to 0, f of x plus h is equal to fx, right? Because of the right hand and left hand limit, right? So this is, you can write this to be f of x plus h to be fx, right? Dt, right? Because of the continuity. That is where we are using the continuity. Okay. So now you take just from with respect to t, you integrate and you get just h fx. Then we have that. So there is the connection. Okay. Okay, so let's move on to our problems today. So let's do a few problems. Let's start with the easy one. Okay, let's start with an easy. So how to do it? This is I mean, not a very difficult problem. So do you remember what Emmett test was? Anyone? What was Emmett test?
Supremum of mod f(x)
Exactly,
actually.
exactly. So she's saying that suppose Fn converges pointwise to F, okay, pointwise to F. Huh? Then she is defining. Lopamudra, go ahead. Mn to be supremum. I mean, these are all defined. I mean, Fn is defined on some D to R. Okay. Supremum X belongs to AB. Sorry, X belongs to D. Then right. So that's how we define Mn. So the result said that Fn converges to F uniformly if and only if Mn converges to 0, right? Right, Lopamudra?
Yes.
So by that direct application, you see 1 comma A, because if you write Mn x, Fn x is x plus 1 by n, okay. So what do you get? So what is limit
We have to find
Fn x? Sorry?
Yes, I can see that we have to find limit function.
Yeah, for a fixed x. For a fixed x, okay. So what will it be? Just take limit n tends to infinity. It will just be x, right? So our fx is x. So what is our Mn, by the way? That is supremum x plus 1 by n, which is Fn x minus x.
Minus x.
That is 1 by, which tends to 0. So that means Fn converges to F uniform. Right? Show that the sequence F square n doesn't converge to F uniform. Okay. Let's see that. That's a very interesting problem. Let's first compute Fn square. Okay. And as you can see, the function is defined on whole R. Okay. The whole R. So these D is R in this case. So what is Fn x? Lopamudra, help me out, or I mean anyone. So what is Fn x whole square? X square plus twice x 1 by n 1 by square. Okay. So that is one. Okay. So now let's see what is fn square x minus f square x. What is that? Because I mean, one thing is clear now. I mean, that is, I think that should be clear, that if fn x converges to f pointwise, it means fn square x converges to f square x pointwise, right? Because of the limiting property. You square it here, you square it there, right? There is nothing much. Okay. What was there? So what was I doing? Yeah. So let's compute fn x minus fx. So what is that? That is x square plus twice x by n plus 1 by n square minus x square. It is nothing but twice x by n plus 1 by n square. Okay. What should be my next step? Anyone? Orpon is here. Orpon, are you there?
Yes, sir.
Give me a hint. How should I proceed? Because see, what are we trying to find? We are trying to find supremum of fn x minus x, right? That is our goal, right? Amen. So, I mean, what should I do here now? I mean, a hint somewhere. Hello? Hello?
Limiting value to n goes to infinity হলে
Yes, anyone? So you see,
I think the supremum doesn't, I mean, it's infinity. I think the supremum doesn't exist.
just a minute. So Ovik is on the right path. I think it is Ovik.
Yeah.
He is also one of my students. So you see, what are we gonna do? See, the intuition is that there is an x involved here. Okay. So the first question should be, what should be my guess? What should I try to show? Should I try to show mn goes to 0? Should I try to show mn doesn't go to 0? What should be my intuition? See, this is your clue. There is an x there. You understand? So it is safe to write that this supremum, this is supposed to be, if this is exist, this is greater than equals to fn x minus fx for all x belongs to R, right? That's true, right? Put x equals to n here. So for each n, I am putting this n, okay? For each n, I am putting this mn. So mn is greater than equal to what? What was this thing? Fn n minus fn, right? What do you get now?
2 plus 1 by n square.
That is twice n by n plus 1 by n square. Just from this line, it is 2. You see, mn is always greater than equals to 2 for all m. Okay, so mn does not go to 0. The sequence is not uniformly convergent. And you see, there is a problem in C. Okay, the product of two uniformly continuous functions, whether it is uniformly convergent function, whether they uniformly converge or not. So you can take both the functions to be fn in this case. You see, fn, they are converging to f, but fn square is not converging to f. Not uniformly, but pointwise, of course. Okay. So that was one of, I think it was, it's quite good problem. I think.
Sir, I have a question. So,
Yeah, go ahead.
the product of two uniform convergent, the product might of two uniformly convergent might not be uniformly convergent.
But what about the opposite, right?
No, I had the question that will it be possible if it is point-wise convergent and the product is also point-wise convergent?
That we just showed. You see, so suppose fnx is that was the whole point, right? That is the whole point. If fnx goes to f and fn square goes to f square, I mean that, okay, let's just simplify.
Oh, I understood.
Yeah. So
Here the fnx is point-wise. So if we take that both to be fnx, then it will be
yes,
product of point-wise to point-wise.
yes. So once you just take this limit, see, for every x, we know that these limits individually exist, right? So you can just distribute the limit. Okay, that is true. It will converge point-wise, of course. I mean, else there is enough. Okay, so let's do some other problems. There was a nice problem, I think. We can do any of 6, 7, 8. Okay, let's do 6 actually. Let's do 6. Let me first copy this problem, just a minute. Oh, just a minute. My laptop is running low on batteries. Just let me switch on the charging button. Yeah. Okay. Actually, sometimes I'm getting a little bit tired because I mean there is way too much humidity in Kolkata right now. I mean, you can look at this. There's 29 degrees Celsius they're showing, but it feels like 40. The humidity is, I mean, so high. So what does the problem say? So if a to b, the continuous function, this problem, okay? So if a to b is Riemann integrable, and if a to b are, capital F a to b are, they have defined in this way, okay? 0 if t equals to a, and 0 a to t if t belongs to open AB. Open A, closed B. Okay, we have to prove that F is continuous. That is one of our problems. The other problem is that suppose A to B suppose A to B to R be bounded and Riemann integrable if they have defined it to be just the way we are defining the antiderivative. Prove that there exists a constant m such that fx minus fy is m times x minus y form. Okay, is f necessarily differentiable on AB? So you think just think for a while. So they are trying to say, see, look at the statement, why the problem is given there. So f is bounded, Riemann integrable, that's it, nothing else is given, not even the continuity. They are saying that this f is Lipschitz function. This f becomes a uniformly continuous function, not only continuous. Okay, so we just showed that the antiderivative will be, for a continuous function, the primitive will be, for the continuous function, the primitive will be differentiable. But here they are claiming that even if the function is not continuous and bounded and Riemann integrable and all those things, f will still have some special properties, like f will be a Lipschitz function. So let's do B first. Okay, let's do B first. So let's do B first. So let's write fx minus fy. What is that? A to x ft dt minus a to y ft dt. That is y to x ft dt. Should I put up? Yes, why not? Then by the probably the most used inequality in analysis, right? So clearly f is bounded, right? F is bounded, it means mod f is also bounded. So there is an m such that mod f is less than m. So you get today we are doing some basic level problems, okay? But we will go to a step higher, a level higher in the next class, and in the last class we'll try to go a level above that. Okay, so that was the first thing. Now what about this? Is f necessarily differentiable? Is f necessarily differentiable? It may not be. So counter example.
I think it is differentiable if f is continuous, like the Riemann integrable function.
Who is it?
If
Tista,
that
I
is
think.
continuous.
Yeah, you are right. So she is saying that we need the continuity of this f in order to conclude that f is necessarily differentiable. That is direct from just what we just did, right? Just what we just did above. That is, that was the fundamental theorem of calculus. Yes, that was it. F was continuous. You see, to write this step, we needed f to be continuous, right? Tista is also a very promising student. So counter example, yes, but that is a sufficient criteria, right? Not a necessary criteria. So it may happen that f is not continuous, still, that entity primitive is differentiable, but we are supposed to give a counter example. So you take fx equals to a step function. Just take a step function 1 for x greater than 0, and -1 if x is less than equal to 0. Okay. What should be your fx? It should be direct, right? What should be your fx? It is mod x, right? It is mod x just, right? See, it is not differentiable. Right? Okay, can there be a follow-up question? Just a minute, let me check. Can there be a follow-up question? Just give me a 1 minute. So, can there be a follow-up question? No, that's right. He just put it off. Okay. So let's do A. In A, we will have to show that Riemann integrable and all these things by this, we will have to show that f is continuous. Okay. So first of all, f is bounded, right? There exists some m such that mod f is less than f. So there is an upper bound. Now, suppose T belongs to open A, close B. Okay. Then if T minus FA, what will be that? Help me out, please. That will be integration A to T fx dx minus 0, right? FA is 0, right? So that is,
Sir,
yes.
sir, it's not given that f is bounded.
Yes, but it is Riemann integrable. Okay.
Sir, is Riemann integrable bounded, sir?
You see, the problem is that you remember how we defined that UPF and LPF? Just a minute. So let me do a rough work there. I mean, is there a space? Yeah. So you define how we define that UPF and LPF. You remember that, right? So if you
Yes,
see, suppose there exists an x naught at which f is unbounded. Okay. Okay.
sure,
Suppose
sir.
f is unbounded. Now you see, P is a partition. So P will have, there are AI, I mean, it will have some AI here and AI plus 1 here, such that, I mean, in this point, f is unbounded, okay, in this interval, right?
Yes, sir. Yes, sir.
Now you see, what will be mi? What will be the supremum? That will be infinity. I mean, if f is positive, right? And if
Sir.
f is negative, the mi is supposed to be minus infinity, right? So you can't define the sum.
Sure,
Okay.
sir. Sure, sir. Okay, sir.
I'm really glad that you asked.
Thank you, sir.
Rather, for P equals to A,
Sorry.
if A is defined to be 0 at T equals to A,
If is differentiable I'm not getting. I mean, can you be a bit louder?
The value of the function is 0 when t equals to a. I think.
Yes. That's why it is fa. I have written a, right? Fa is 0. I mean, have I written anything wrong?
It belongs to closed A. Okay. Then we can take the unmeasured of it.
I mean, it doesn't matter because even if you take, I mean, t belongs to closed AB, it doesn't really matter. You see, the fa will still be 0. Okay.
Yes.
Yeah. Okay. So that is less than equal to what? Integration a to t mod fx dx. I mean, who was it who asked the first question? There was a girl.
Yes, sir.
I mean, may I know your name?
Zunaida.
Okay. Carry on good work. Okay. And keep up this habit of asking questions.
Thank you, sir.
That will not only help you grow in mathematics. I mean, that helps the civilization grow. Schools follow. Smarts ask. Okay. So a to t fx dx. What then? Yeah.
Sir, here we can use that part from above. You have said that there is an m part, right?
So you are
So
writing that, right?
yes, then we can also, I mean, change it into m into b minus. Oh, there's a t. So t minus a, and if we shift it right below that left hand side, and we can assume that yes. I mean, if we then send t to a, then
Yeah. So of course this is 0,
above that,
right?
yes.
So ft minus fa modulus is less than equals ft minus a. It goes to 0 as
As
t tends.
t tends to a.
So f is continuous at a. That's right. So f is continuous at a. And for the other part, what should we do? The technique is just very same. Okay. So let C belongs to AB. Okay. Open it. So what will be ft minus fa modulus? What will be that? It will be nothing but a to t fx minus a to c fx. I keep forgetting writing dx. Okay. So that is what? C to t fx dx, right? That is less than equals to c to t right? Oh, I wrote a there. Again, you take t tends to c. Okay, so this tends to 0. So this tends to 0 as well. So ft tends to fc. Okay, this is a good problem. I think this is a good problem. Let me see if we can do one more.
Excuse me, sir.
Yes, sorry.
A small doubt. In the previous problem, shouldn't we prove that the capital F is continuous using limits?
Sorry,
In the previous problem,
just a minute, just a minute. Yes, please. Previous one means 6A, right? This one.
6A.
Yeah.
Shouldn't we prove the continuity using limits? If limit and functional value are same. I feel
Yes.
this method is a bit lengthy. I'm just asking whether we can use it or not.
What are you trying to do? I mean, what is
So
your approach?
my approach is the value of value of F at A is 0. And left hand side, we don't define the function, so we can leave it. Right hand side, the function value is defined to be the integral. So when I take the values on the right hand side of A, it is also 0. So I conclude that limit at A and functional value at A are same. So can I conclude that F is continuous by this method?
That's what we have done, you see. But in a bit more bit more rigorous way. I mean, whatever you are saying, once you try to write it down, this will go down this path. We have done exactly what you're saying, but I mean, you have to write it still. You understand that?
Okay.
Because yeah, I can understand what you're saying. You are saying that this is direct. I mean, A to T.
Yeah,
once
integral
T approaches to A, once T approaches to A, it goes to 0. I mean, that is all fine, but still they will expect these things. Okay. This is just a better way to write, nothing else. Because you see, I mean, let me give you an inside information. I mean, so suppose there are biases, right? Whenever a paper checker is checking a paper, there are bias. Okay. So suppose you have a question paper from question 1 to question 8. Okay. You will have a tendency that whoever has done the first question brilliantly, you will tend to give him more marks. And whoever has sort of, what should I say, maybe a little bit messy on the first question, you will tend to give him less credit for the next questions as well. Okay. That's a human bias. Okay. Because I mean, you might think that it won't make much difference, but I can tell you, you can. There is a book of Daniel Kahneman. Okay, you can go through it. Thinking Fast and Slow. He made this experience on himself.
Yeah, I have read it. It's wonderful book.
You have read it, right? Yeah. That's a famous book. So he read it actually. So there was probably, say, I mean, 50 students. So he first checked their copies. I mean, one by one. So first student, question number 1 to question number 8. Second student, question number 1 to question number 8. He noted down the marks. Okay, he noted down the marks out of 50. Then what he did, he checked question number 1 for all the students. Then he checks question number 2 for all the students, and he found that there was, I mean, a considerable difference in numbers. Okay, and this experiment gave rise to a branch which calls behavioral economics, right?
Yeah.
So what is your name, by the way?
I'm Revati.
Sorry?
I'm Revati.
Okay, Revati. Okay, so to get rid of this bias, what CMIs and TIFRs and ISI do, I mean, they have a very scientific method. What they do is that, so suppose you have 200 students, okay, and they have given question number 8 to question number 1 to question number 8, okay. So what they do is that the professor who checks question number 1, he will be checking the question number 1 for all the students. Whoever is checking the question number 2, he will be checking the question number 2 for all the students. So you realize you won't, I mean, have the opportunity to make an impression. So it's better that you write in a, I mean, more rigorous way. I mean, that's all.
That's it.
Okay. Just a minute. Let's see if we can do this one, or maybe this can be lengthy, or maybe we can do some easier problems. Just let me think. No, this shouldn't be much lengthy actually. Let's try to do it. So Fn is a sequence of continuous real valued function on 0, 1, converging uniformly on 0, 1 to a function f. Suppose that for all n greater than equals to 1, there exists xn, so that Fn xn is 0. Okay, fine. Show that there exists x belongs to 0, so that fx is 0. Okay. Okay. There is a more generalization of this question, you know. Sometimes what they do, they will tell you that suppose xn converges to x, okay? Just a generalization. I'm not doing this, just I'm for the generalization. And they will tell you that fn converges uniformly to f, okay? And they will let you show that, they will ask you to show fn expressions. That is also, you see, this is a more generalization of this particular problem, now. Okay, let's solve 8a. So, sorry. So there is an xn, right? So 0, 1 is compact, right? 0, 1 is compact. So by Bolzano-Weierstrass theorem, this xn has a convergent subsequence. Convergent subsequence. Xn k maybe. And say it converges to x, okay? Limit k tends to infinity to x, okay? So suppose for some x belongs to 0, 1, okay? So you see f is continuous, right? Since f is continuous, so take epsilon greater than 0. No, for the time being, let's first use that. For the time being, let's first use that f is uniformly continuous. Okay. So f is uniformly continuous. Since fn is, sorry, not f uniformly continuous, fn goes to, I mean, f is also uniformly continuous because continuous functions uniformly converging to f. So, but what we are doing is that since fn goes to f, you see, you remember that mn, that sup fn minus f.
Sir, I have an idea. May I proceed?
Yeah, go ahead.
Sir, here it is given that fn xn is equal to 0, right? So,
Is
as you
given
have
that
stated,
fn xn.
as you have stated before, that we are taking at smaller, I guess, subsequence, which is x and k, which tends to x as k tends to infinity. So, if we can somehow write it as fn xn minus f of xn, and try to show it like that. I mean, what I'm trying to say is,
I'm on that path. We will be doing exactly that.
yes, I'm just saying that if we can somehow show that part, then for fn xn is being 0, it will eventually give us that fx equal to 0.
Yeah. We will be doing exactly that. Just using this epsilon definition. Okay. So you see that mn, which was sup of fn minus f, this should go to 0 as well because that was an if and only if condition. Fn converges to f uniformly, if and only if mn goes to 0, right? So mn should be less than epsilon for some, for all, for epsilon greater than 0. For epsilon greater than 0, there exists n such that is less than epsilon for all n greater than equals to, right? Because mn tends to 0. So what will be that? You write it down, that supremum Fn t minus Ft is less than epsilon, t going to 0, 1, right? This is 1, okay? You have it. Just keep it in hand. Now, you take mod fx and k. Can I write it? If xn k minus fn k xn k plus fn k xn k. Yes, that's something we can write, right? Is that clear? Now you see, if n xn goes to 0, right? If n xn goes to 0, right? So for this epsilon, we will get a k naught such that fn k xn k modulus is less than epsilon whenever nk is greater than k naught, right? Right? So if you put that k greater than equals to k naught, what do you get? This supremum is always less than epsilon. The supremum is less than epsilon. It means, what does it mean? So k is greater than k naught and n. Okay. Then both this inequality will hold. Both 1 and 2 will hold. So this thing will be less than epsilon. This is strictly less than epsilon. And this is also strictly less than epsilon, right? Okay, I mean, if you want to do that, you can just do epsilon by 2. Okay. That's not a problem. 2 epsilon is good enough. Okay. So there it is. Okay. Now we were asked to show fx is 0, right? Just take the limit inside. Because f is continuous. Why is f continuous? Because fn are continuous and fn converges to f uniformly. You take the limit inside and put fx. Okay? Clear? We don't have much.
Yes, sir.
Let's move on to B. So once the class is ended, okay, once the class is over, I will ask you guys to give your honest feedback, okay? To because this is the first time I'm taking such a class on an open forum. I have been teaching for the last decade now, but this is the first time I'm taking this on open forum. Okay. I mean, this is a discrete class. I don't know you don't know the students. I don't know, I mean, their background. I don't know, I mean, how much capable they are. So I request you guys to give, I mean, sir, honest feedback. Just a minute. Let's read the problem first. So Fn, they have given it x to the power n times cos 2 pi nx. Just give me 1 minute. Let me take some water. Just. then for which x the limit n tends to infinity fnx exists. Okay.
Sir,
So you
for
see,
x equal to 0, it might.
okay, so that is one. I'm saying that just put x equals to x equals to 0, and then it's obvious. X equal to 0 is one choice. Okay, so let's choose. So this was say case 1, case 2. So case 2, mod x is less than 1. Say now you see fnx is what? Mod x to the power n mod cos 2 pi nx, right? And we can write that this thing is mod x to the power n, right? And you see this goes to 0, right? Because mod x is less than 1. Since mod x is less than 1, we can write, I mean, I should write for each x. For each x, this goes to 0, right? For each x. So clearly, so if x is less than equal, mod x is less than 1, then also the limit exists. Okay. So case 3. What about if x equals to 1? So we are about to check x equals to 1 and minus 1. Okay. So please tell me what is fn1, that is cos 2 pi n, right? What is that? That is 1. So there also the limit exists, right? And what is case 4? X equals to minus 1. What is fn minus 1, by the way? Now there the limit doesn't exist, right? Cos 2 pi in x, I mean, this is just minus 1 because cos of negative 2 pi n is 1, but this is minus 1 to the power n. So the limit there won't exist. The limit doesn't exist. But is there a follow-up question? I mean, can we draw something from there? Just a minute. So you see, whenever, so fn xn is 0, no, that's pretty much it. I mean, there are sort of these counter examples. I mean, they will probably, I mean, see, the question will come in disguise. So they will not probably give you this function. Okay. They will just omit this function, and then they will tell you that fn is a sequence of function. Then when can fn x exist and something like that. Yeah. Hello. Hello. I can't hear you.
Sir.
I can't hear you.
I have a question that should we not also check for minus 1 less than x less than 0 part?
No, the domain is there. No, right? The domain is there.
No, I am saying that it is from minus 1 to 0. I mean, we have already checked for a modulus of x.
No, yeah,
oh, no, I have understood. It is already done in case 2.
Okay, so we will be concluding today's class. Thank you for your tolerance. That's all I can say. I only have gratitude, okay, for you guys. You have been so patient for this long. I'm sending the notes and the recording, okay?
Okay, thank you, Abhirup, for this nice session.
So, sir, I don't. Okay, sir, that's your gratitude to call this session nice. But I think the jury should be. I mean, the students are there. They will pass it. Let them decide whether it was at all, or did they think that we just wasted the 1.5 hours of our life. Let them decide.
Yeah, you're right. But yeah, I think.
But I will ask for your, I mean, valued opinion. I mean, what do you think? Was it good? Was it okay? Was it not so good? I mean, I will just ask you for your suggestion.
Yeah, the session was really good with lots of interactions also there, I think. Yeah, as it is a holiday, I think some only few, around 40 students were in the beginning. Now I think 25 were there. So as this many people have stayed throughout the session, means that they are really enjoyed it.
Yes, but I mean, you are the one who is, I mean, more experienced here, I mean, than any of us, and more knowledgeable. You have been loyal to maths more, I mean, more than whatever, I mean, more than the length of our lives probably. So if you think that it was okay, then I will just
Yeah,
believe.
actually, I enjoyed the session with, your explanations are really good, and the way of teaching is also nice, I think.
Yeah, the only problem yes, sir. The only problem I have is that, I mean, I tend to be the spontaneous. I mean, I just can't follow a structured note somehow. I will probably have a structured note. Then the class, I think, should determine itself. I mean, which paths to follow, depending on the interaction, depending on the follow-up questions. I mean, suppose I have a solution there, and suppose some student is, I mean, going for another approach. Once I do that, this approach should give rise to another question. I mean,
so we cannot cover the portions that we have planned in the, earlier. So that may happen, but that is actually good also. In some sense, it is good. Dear participants, feel free to share your feedback, and if you have any queries, you can ask it now.
You are free to ask absolutely anything. Just excuse me for a while.
Participants, feel free to share your feedback, what you have seen.
Sir, I think they can be more honest once I am not in the session. I mean, that's a barrier. I think that's that's a natural barrier.
No, it's not like that. We usually used to have this pattern. I think, because many people are very shy to speak.
Yeah, that's why I was saying maybe
even in the online meet.
Yeah. Even if you, I think you can ask for just a feedback in the groups. Maybe a polling session that it was good, very good. I mean, there they will be. I think they will be more free to say. I mean, because here is an interaction. Because once they give an opinion, I can have a counter question that why do you think that? They are probably afraid of that interaction. So it's good that if they are just free to provide, free to say their opinion. I mean.
Anyway, I will ask someone to share the feedback.
Of course.
Revati, could you say something about today's session?
Sure, sir. Actually, the session was very wonderful. I learned a lot of new things. Actually, I'm trying to clear CSI net. So my point of view will be like, what could be the shortcut to solve the problem? But you explained it with something that is deeper than that.
You are trying to crack what? Sorry, I didn't get the examination. You are trying to crack what?
CSIR net.
CSIR net. Okay. So your approach is good actually, but I mean, since this is a math session, I had to just write down the solutions.
I understand that. That is what the thing I said. Instead of going with the shortcuts, you explain what is actually running behind it. That was really wonderful, sir. And my expectations would be like, if the questions were related to CSIR, it will be helpful for me. But I understand there are people who are preparing for the other exams as well. We need to cover up for everything. So I would expect to have an MCQ session in the future.
Okay, so you see, I will definitely try to conduct a few series, because I don't believe in those 1 or 2 discrete classes. I think at least there should be 3 or 4 so that we can cover something. But I mean, see, the math is right there on the horizon. It is right there after 2 or 3 weeks. So it was like a math focused session. Okay, there will be net focused sessions as well. I mean, after a few months before the CSIR net, let the notification begin. Then I think me and sir can discuss something.
Okay, so thank you so much.
Okay,
that means
thank you. Because you see, I mean, why the explanations are needed. After clearing the CSIR net, once you go to the interviews, they will give you a pen and they will ask you to write the solution on the board.
Yeah,
you can't just ask for options everywhere. But again, clearing this MCQ sessions, I mean, these are bread and butter for us mathematicians, and you have to clear it to run your stomach. I mean, that's it. It's as simple as that. To get your stipend, your knowledge is not enough. You have to get your accuracy. You have to get your speed right. I mean, I will tell you that I have cleared ISI, TIA for those written. Okay, my all India rank was probably around 12 or 13 in the ISI written exams. PIFR, I was inside the first 26. The most, I mean, the hardest time the exam gave me was CSI and net. Because there were so many questions, and that was I mean, I had so much, I mean, so less time to think. So speed is something you need to acquire. I mean, at least for the next 6 months. Okay. It was nice to talk to you. Yeah. Thank you.
Thank you, Revati. It will be good if you could introduce yourself.
So I'm Revati. I'm from Tamil Nadu. I have completed MSc BEd. And right now I'm focusing on CSI net and other exams, state level exams. This math aspirant platform have been a very good source for learning, and to say simply, this means a lot to me. Thank you so much.
Okay, thank you, Revati. And remember that, see, these type of discussion sessions, even though not actually discussing the MCQ or MSQ type questions, still the inputs that you are gaining from here will be really helpful to widen your thoughts and also to strengthen your concepts and understanding level. That will be definitely helpful in clearing any of these type of exams.
Yeah, I think this is a basic. I mean, this is a basic. I mean, it will help your cognitive ability to grow up. I mean, that's the basic. The brush up is the MCQ part. Just give mock test. Just give mock test. That's the only way. Read textbooks. I mean, that's how I teach my students. Read textbooks first. I mean, how did we prepare when we were in school? R.D. Sharma, R.S. Agarwal, pick up a textbook. We completed it. Then our teachers gave us, I mean, probably a reference book. We completed it. Then go for the previous years. I mean, then go for the test papers for the PVIQs. That is the only way to do it. The school level type, that was actually the way to do it. But somehow when we go to CSI and net, because we have, I mean, much less time. I mean, most of us come from probably a certain background. We have a burden of earning money. What we try to do is that we just go through the theory in a hurry. Then we try to just step our way forward or jump our way to directly to the PYQs. That's never the way. I mean, you cannot expect yourself to solve NCERT and then go to the IIT JEE level directly. No, that's not how it is done. It's not scientific. So I would ask you guys, everyone, I mean, with my limited knowledge, do science in a scientific manner. That's all.
Yeah. Okay. Okay.
Okay. That's, I think.
Okay. Yeah, Shruti Radhakrishnan shared the feedback in the chat box. I think Abhirup can read it.
I read it.
Yeah. Okay, any others who would like to share a feedback? Please do it now. I think Devdeep Ghosh share something. Are you there, Devdeep Ghosh?
Yes, sir.
Please introduce you first.
I am myself. I'm just a regular undergraduate student. I have completed my BSc Mathematics, and now I am trying to compete for ISI Math.
So you are from West Bengal.
Yes.
Yeah,
Sir.
I mean, I know this. I know that dialect. It's very similar to mine. Once I hear it, I know that.
Yes, sir. I am from West Bengal.
Yeah. So what's your name, Devdeep?
Yes, sir.
Okay, so I think we can. So I have planned some sessions, but I'm open to your suggestions. So if you want, say if you want me to take 1 or 2 classes on a certain topic. So I am suppose I am going forward to take a classes on, say, Riemann integration and sequence and series of functions. But suppose you think that, sir, how about continuity? How about differentiability? Why not a few problems on multivariate calculus? You can give your input as well. You can give your input and you can give me 2 weeks. I will prepare something and then discuss the timing with sir. That is also, we are open to that. I mean, don't think this is never a one-way communication. This is not a dictation. This is supposed to be a discussion.
Okay, thank you, Devdeep. Yeah, of course. And Abhirup, I think you could share some information regarding your institution as well. I think many people don't know much about your institute. Yeah, if you are not ready to
No, I'm ready, but
now,
actually
you
I'm a
can
little bit.
do it in the coming session as well, because I
I
think
can just brief it for 1 or 2 minutes, because you see, I mean, it's sometimes we Bengali, sometimes we feel a bit shy whenever we have to, I mean, blow our own trumpets in a while. So in a way, okay. So I am doing my PhD in algebraic geometry. This is, I'm doing it from TCG CREST. I will ask you guys to just check. If possible, I will send the link of my institute there. You can just go and have a look at the departments. I mean, this is a new institute, and in the applied science, they're really making, I mean, advances, because they are the first ones to make, I mean, to create. They are creating quantum computers with the collaboration with IBM. So this is the first one. This is funded by Haldia Petrochemicals. TCG stands for the Chatterjee Group, which is the chairman is the Dr. Purnendu Chatterjee. So I'm doing my research there, and this is what should I say, an institute which is similar to CMI. I mean, we all know that the people like Sheshadri and Balaji, those stalwarts, they came out from TIFR. They established CMI because they thought TIFR was way too research oriented. They wanted to teach people. So TCG is a similar institute. It has been founded by the likes of Dr. Bimal Roy, who is an Padma Shri, ex-director of CMI. Rajiv Karandikar, ex-director of, Bimal Roy was ex-director of ISI, Kolkata. CMI, Rajiv Karandikar, ex-director. Professor Gautam Mukherjee from ISI, Kolkata. Professor Rana Bodua, retired professor. Vasudev Das is there. I'm only talking about, I mean, the cryptology and mathematics and probability department. There are, I mean, there are stalwarts everywhere in our institute. They are trying this new institute because you see, we have far too many good students and far too less good institutes. So it's always good if we see the professors are coming out. So they are doing that. I'm doing my PhD there. Okay, so I will. You can have a look at the faculty profiles. And on my institute, whatever I am teaching, I started to teach CSI and NET sessions. I have been teaching it informally. I mean, for 2 or 3 years. I started to teach it formally since the last August. I mean, the last NET. So we are having 4 courses for the timing. For the timing, one is NET, another is NET plus PhD, which means NET plus the other PhD exams like CSI and NET, I mean, PhD, TIFR, ISI, and the interviews as well. And similarly, for the BSc level, we have JAM, and then we have another JAM plus MMath and TIFR. So that's it. I mean, we can talk in detail for 5 minutes in the next session. That's the brief.
So, Abhirup, one more thing. Is your institute offering, apart from PhD, offering masters as well?
Offering masters as well means? Oh, okay. The one where I am in.
Yeah, TCG.
So they have started with postdoc. They have come down to PhD. They will start MSc, I mean, in a while. I mean, this was supposed to be started from this year.
Currently having only PhD and postdoc.
Yeah. The academic, from this academic session, they were supposed to start it, but there was something, I mean, some formalities going on with UGC, which is taking a bit longer than usual.
Okay. Anyway, thank you, Abhirup, for this.
Let's Study is for the time being for the next of my academy. I mean, for my teaching academy, the name is Let's Study. That's
okay.
Okay. Let's do something.
Okay. Thank you, Abhirup.
Thank you, sir, for giving me this opportunity. Thanks, all of you, for tolerating me for this long.
It's okay. Thank you. So all the very best for your research and all that, and let's hope that we can have more sessions in the coming weeks.
We will definitely do that. Okay.
Okay. Thank you, everyone. Let us wind up here. Bye bye. Good night.
Bye.